of you already on the line, thank you for joining. We'll be waiting just a couple of minutes to the top of the hour to get started. Okay, it just turned the top of the hour, so let's go ahead and get started. Good day, everyone. I'm Jason McDowell, Chief System Integration Officer for the Energy Systems Integration Group. It's nice to see you here today, and would love to warmly welcome you to one of our monthly eSig webinars for October. For those of you not familiar with eSig, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials across the industry. eSig also serves in a leadership role with the Global Power System Transformation Consortium, or the GPST, whose mission is to bring together key actors and catalyze a rapid clean energy transition at an unprecedented scope and speed. eSig leads the first of 5 pillars, which drives the research agenda for all the system operators. It was also great to see all of you that were able to attend the Fall Technical Workshop last week in Providence. So very many new rich topics and discussions happening in our industry. It's hard to keep up with it all. And record-breaking attendance at our workshop to boot. It just shows proof that the energy systems integration topic is one of the coolest and most popular subjects around. Our workshops and monthly webinars are open to everyone, so please feel free to register at any time at the eSig website. And if you're new to eSig, I strongly encourage you to follow up with us if you like what you hear, and I hope that you do. eSig membership will give you an opportunity to participate actively in all of our working groups and task forces, and you can find us on the web at www.esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Before I hand it over to today's star of the show, I just wanted to share a few logistical items before we get started. First of all phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we're going to use the Slido platform. And to ask your questions, please go to slido.com and enter the participant code ESIG28. That's ESIG28 as the event code. The instructions are also at the bottom of this screen. Everyone can vote using a thumbs up button next to the questions to escalate and prioritize the questions that you'd like to have asked. We plan to save about 10 minutes or so at the end for Q&A, and then we'll wrap it up at the top of the hour. And we'll email a link that will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions at the webinar. So feel free to ask your questions, and we'll be sure to get those answered. Today's topic offers an overview of ENTSO-E's grid stability initiatives to address how grid stability is ensured in a changing power system. We all know that with a rapidly evolving power system, stability challenges have also evolved. In the European context, ENTSO-E, as a network of collaborating transmission system operators, tackles these stability changes at both a regional and a European-wide scale. This webinar provides an insight into how European TSOs tackle these stability issues, what the latest modeling and simulation techniques are, and you'll also learn how stability is analyzed through recent case studies and demonstrations, and what the future research needs are from a European context. Here to talk with us today about it is Knut Styve, a special advisor for the Research and Development and Innovation Department at Statnett, the Norwegian transmission system operator. Knut received his PhD in electrical engineering from NTNU in Trondheim, Norway. He also works for RDIC under ENTSO-E's under ENTSO-E in Europe, and is convener of the Stability Management in Power Electronics Devices workstream, a part of ENTSO-E's Working Group 2 on Security and Operations of Tomorrow. So just a short reminder once again, use slido.com for questions with event code ESIG28. And let's get started. Knut, looking forward to your webinar, and now I'll hand it over to you.
Thank you very much, Jason, and thank you very much for the invitation to hold a presentation here today. First of all, can you see my screen?
Yes, we can see it now.
Okay, thank you. As you said, I'm going to talk about how is grid stability ensured in a changing power system, and this will be in a European context. I will do this presentation on behalf of ENTSO-E, the Research Development and Innovation Committee, RDIC, and the work group number 2, then Security and Operations of Tomorrow. We also have support then from the SPD group, System Protection and Dynamics. Contributors to this presentation has been Dr. Yannick Massmann from Amprion, René Suchamp from 50 Hertz, Uri Pestana Joao Moreiro from REN, Rede Electricidad Nacional, and from the ENTSO-E Secretariat, I have support from Arvind Daxinamurti, Gonzalo Morolon, Tetiana Takchuk, and Francesco Celossi. And all those have been crucial then to be able to put together this presentation. The first part, I will give you an introduction and a context then for the ENTSO-E Vision 2050 and the RDI roadmap. And I will pick up some and tell you about key stability phenomena that we are looking at, and grid stability challenges with increasing renewable energy penetration, and some examples then of challenges that have been observed so far. In the part 2 then, I will tell you about ENTSO-E actions, among them modeling and simulation techniques. I will go into grid forming converters and their role in enhancing stability and instability analysis, and I'll also tell about future directions and research need about these topics. The ENTSO-E, that is the network, European network of transmission system operators for electricity. We are representing then 40 TSOs across 36 countries in Europe. And we are serving about 500 million citizens, responsible for the secure and coordinated operation of Europe's electricity system. We are also a common voice then of TSOs in Europe, and we serve the interests of the society. We lead the coordination of efforts across countries to enable a successful energy transition. And ENTSO-E initiatives initiates activities and projects needed for the green transition in Europe. So then I'll go into the context of stability issues and challenges in the European context. First of all, the vision that we have is to build a resilient, secure, and affordable power system. And we will integrate renewable energy at scale, aiming for Europe to be the first climate-neutral continent. And stability management and innovation are central to the energy transition. So the ENTSO-E roadmap provides the blueprint for success on these topics. The roadmap focuses on achieving a carbon neutral Europe and emphasizes innovation in grid management, digitalization, and cross-sector integration. It supports the European Union's Green Deal objectives, and among the different clusters that we are working with, power grid, enhancing grid use and integrating renewable energy. Cluster number 2 then, we have the digitalized power system, ensuring secure hybrid AC/DC grid operation. And cluster number 3 then, integrated systems on fostering cross-sector flexibility and market integration. As you can see from the slide then, energy system flexibility, operating future grids, infrastructure and investments, and market design and innovation will lead the way then for a power system for a carbon neutral Europe. I assume that most of you know the challenges that we are facing from now and into the future. The generation units' inherent properties are different. We are going from fast, heavy generator rotors to power electronics connected in-feed. So reduced synchronous generation is leading to lower inertia and increased volatility from wind and solar generation will make it more challenging to operate the system. So while the solar and wind offers then environmental benefits, they reduce the synchronous generation, which is connected at any time, and which provides then inertia, and it is crucial for maintaining frequency stability. Furthermore, their variability introduces volatility into both generation and demand, making both voltage and frequency stability a constant challenge. Just a quick look on the power system stability phenomena, the old ones and the new ones. And I guess most of you have seen figures, which resembles this one. On the right-hand side, we have the rotor angle stability, voltage stability, and frequency stability. Those are the old phenomena that we are used to handle, but they are growing in and changing due to the increased penetration of power electronics interface devices, and they have a time frame of seconds. That's very important to know that, okay, we have some time to handle them, and we have measures to handle them. On the left-hand side, we have the new phenomena, resonance stability and converter-driven stability. And these new phenomena has a time frame of milliseconds. We all know that power electronics either generate or consume energy according to the three-phase sine curve. And when you generate, you have to do it in the same phase and the same way as a synchronous generator. For this one, case stability phenomena, we have some factors that is destabilizing the grid. That is listed up on the left-hand side. To handle that, we have to have measures which function as stabilizing factors. To be able to calculate and to simulate, we need new simulation techniques and models to handle that. We also need better observation, better possibilities to observe, to monitor and control the stability in the system. Due to the less controllability of the new renewable resources, we need controllable resources and flexibility from the demand side of the power system. And we need grid forming capabilities of power electronics, and we need interoperability. And if those measures are not enough, we need synchronous generation to handle the challenges that we meet. So, we need more system services then for stability management, and possible approaches then to system services and matching then the time frames of the new phenomena. We can look at those system services that can be activated up to 1 second, and which can be a response for fast transient states. We have the inertia, and we can have fast frequency results which can react within 1 second then. And we have the damping of power system oscillation measures. And for the reactive power voltage control, then we have to have a dynamic voltage control, fault ride through, override through, lower ride through, and provision of short circuit power then, so the protection will function as expected. Activation time more than 1 second. We have the usual reserves then, automatic frequency restoration reserves and frequency containment reserves, and load reduction and demand response then. And we also have the voltage and reactive power control. Case stability phenomena, to be able to monitor, to be able to observe. Then we need to do it on a wide area scale. It's a drawing of the Nordic system. That's because I worked in the Nordic system most of the time. But of course, it's valid for the whole European system, integrated system. PMUs, will play a significant role then. And those will give you a finer time resolution, 50 measurements a second, versus usual SCADA system, which has one observation for each 10 seconds. It's done in real time, and it's synchronized. Every measurement has a timestamp, which is synchronized with the other measurements in the system. I'll give you some examples from the European system now. And one incident that happened on the 24th of July 2021, and the Iberian Peninsula was involved in this incident. It was a situation where there was a power transfer of approximately 2,400 megawatts from France towards Spain. And a wildfire tripped a double circuit, and consecutive overload of the third circuit, then the system split. The low flow shifted to the west end, and overloading of this Argia Cante grid circuit. And after this disconnection, point of no return was reached, and both parts of the power system became asynchronous. And this led to further both actions and results in the power system. One of the first things that we can observe is that there were huge variations in the frequency and voltage during the events. And there were huge variations in phase angle, active power transfer, and phase angle differences. So on the two figures on the right hand side, we can see that between what was defined as event number 2 and 3, there were a lot of undervoltage situations in the grid in the northern part of Spain. And after event number 3 and the splitting, we can see that there were huge overvoltages in the system, in the Spanish 400 kV network. So this grid stability challenge was that, okay, we observed ROCOF, rate of change of frequency, in Spain, Portugal, with a maximum gradient then of about 1 Hertz per second. And it dropped, the frequency in the DIR was 48.7 Hertz. The ENTSO-E grid was had a smaller impact on the ENTSO-E grid, where the frequency increased then to 50.1 Hertz. And there was a system defense plan in Spain, Portugal, and the frequency was stabilized by this the measures that was activated. One of them was disconnection of pumped storage in pumped operation, approximately 2,300 megawatts in Spain and Portugal. Under frequency load shedding, approximately 4,800 megawatts in Spain and Portugal. And activation of primary control, approximately 370 megawatts in Spain and Portugal. And I can also mention that the share of wind and solar generation in France was about 15%. In Spain, it was about 55%. In Portugal, 58%. And this is said to be a close call for the power system in Spain and Portugal. Other challenges that we can observe with the increase in renewable energy penetration is an increase in oscillations. East-west oscillation in continental Europe, it's a huge power system in geographical huge. And it has been observed that trip of generation may cause oscillation. And Portugal and Turkey are in opposite mode. And you can read more about it in the in public documents. Then. Another example, east-west oscillation in continental Europe, opening a circuit breaker near the tie lines may cause oscillations, as shown here. And we can see that if you look at the phasers down to the right, on the right-hand side, you can see the Iberian Peninsula and Central Europe are almost opposite, and Greece and Turkey are in the middle there. And east-west oscillation in continental Europe, hybrid interconnected system with HVDC link in AC mode keeps the system oscillation forever. And it's necessary with alarms from the weather monitoring system to the SCADA system to alert the operators of the situation that have occurred. If you look at the phasers on to the right, you can see that Portugal, Spain, and Turkey, Greece are in the same mode, while Central Europe is in the opposite mode. Very interesting. And lately, the East and Center and West mode has become the most frequent oscillations mode after the expansion of continental Europe to Ukraine. So you have a mode then, as seen by the phasers down to the right. Portugal and Turkey are in the same mode, and Central Europe in the opposite mode. And you can also see some of the phasers down in the slide here, where you had the Iberian Peninsula and Turkey and Greece in the same direction, and from Central Europe then in the opposite direction. This is an example from a Norwegian wind farm. It's a very small example but a wind farm in voltage control mode started oscillating, and it was necessary to reduce the infeed from the wind farm to stabilize the system. And it was the reason for this instability was traced to a sampling frequency of 80 milliseconds for the voltage. And that's a sampling frequency of 12.5 Hertz, which gave an oscillation of 6.25 Hertz. Easy to mitigate if you know what to do. Then I'll go into the ENTSO-E initiatives and interest in tackling stability challenges in the future. ENTSO-E has developed a new roadmap, a research development and innovation roadmap for 2024 to 2034. It's a roadmap to accelerate the development of the future power system, a system that needs to be sustainable, flexible, digitalized, and at the core of the European energy system of systems. So you can go into the different boxes here, and there are three actually topics: modeling and simulations. That's very important then to be able to calculate, simulate, and find the challenges before we try to build anything or try to build capabilities into the different assets connected to the grid. The left-hand side, grid stability and grid forming converters. That's necessary to keep the system stable as a substitute for lack of inertia. And system plans, updated codes and procedures are also crucial to ensure a secure and stable operation of the hybrid AC/DC grid. Modeling and simulation techniques. We have to be able to simulate, not only in the time frame of seconds, but in the time frame of milliseconds. We need a wider monitoring to be able both to observe what's happening and to validate the simulation models that we are developing. We also want to predict, detect, and track onset of instability, and as well as additional operational insights to deal with this issue. So what are the relevant models and simulation tools to be assessed to tackle new stability phenomena and be able to calculate what's happening? What specific phenomena can be evaluated? For example, control system dynamics and SSCE. Which is the subsynchronous control interactions in the system. And we can see that we can have a torsional interaction and in different during different incidents then. So, yeah. In continental Europe, there is we are afraid of system splits in the system, and that roll-offs above 1 Hertz per second will occur. So that's very difficult to handle then, roll-offs of that magnitude. So we have initiated project inertia phase number 1 and phase number 2, which will come up with recommendations and what to do to keep the roll-off above or below 1 Hertz per second. The studies have revealed that stability challenges associated with reduced inertia will intensify in the 2030s and beyond. So in the projects inertia, number 1 and 2, will emphasize the importance then of both preventive measures and foundational measures. While preventive measures such as operational strategies and asset-based robustness can help mitigate risks, then foundational measures involving power electronic assets like synchronous condensers, STATCOMs, and energy storage system are crucial for ensuring grid resilience. And by combining these approaches, we can effectively manage the challenges posed by a low inertia power system under system split conditions. So the project ENTSO-E analyzes system splits on future low inertia configuration of continental Europe, following different TYNDP 2022 scenarios. TYNDP is 10-year network development plans, which is development for the different regions of the European system. And cases where subsystems both exceed 1 Hz per second operation threshold shows significant increase from 2030 to 2040. And to avoid blackouts from global severe splits, additional kinetic energy of minimum 72.7 gigawatt seconds in a first no-regret step is required for the regional group continental Europe and Central Europe synchronous area level. And power pack modules with grid forming capabilities, as well as synchronous condensers that comes with grid forming capabilities and storage, are necessary to achieve this goal. We have recently started the project Instability Detection Technologies in PEID systems. To maintain a reliable and resilient future power grid, detection of instability phenomena through wide-area monitoring is needed. Predicting, detecting, and tracking onset of instability is needed, as well as actionable operational insights to deal with these issues. So the questions the project tried to answer is what measurement-based detection technologies can be identified and evaluated for better detection of grid instability. What are the strengths and weaknesses of measurement-based detection technologies employed for different stability phenomena? What are the key factors that influence the effectiveness of these technologies? And what are the future areas of research and development within instability detection technologies? We have developed a position paper, Stability Management in Power Electronics Dominated Systems, which is a prerequisite to the success of the energy transition. There we have some medium-term actions which are started or ongoing, and some that is to be considered. And we have also some long-term actions that will be considered and started in the future. So, the European Commission, they have started or created a program, Horizon EU, that is an innovation program, research and innovation program that is going from 2021 to 2027. And the total, let's see, the total funding for this Horizon Europe projects is about 95.5 billion euros in this time period from 21 to 27. Of course, ENTSO-E is into this, are involved, and the progress is followed by the ENTSO-E Research, Development and Innovation Committee. 5 projects are listed here. Interopera, which will define technical frameworks and standards to make future HVD systems mutually compatible and interoperable by design. So multi-thermal, multi-vendor, multi-purpose real-life projects in Europa will be made. HVDC-wise, design and validate HVDC-based grid architecture concepts. Prosecco, remove barriers to the development of a reliable and efficient hybrid ECD grid. Interscada, a comprehensive strategy to address the challenges faced by TSO and TSOs involving the development of the modular Interscada platform. Advanced algorithms for real-time monitoring and control. And we had the Daedalus, which the goal is to develop and test in realistic demonstrators, environment, innovative tools, granting grid stability and reliability. So ENTSO-E are involved here, and we are following the progress and see if there are, and find out if there are gaps to be covered in the future. So our values define who we are, and of course we want to be to deliver the highest standards, and we trust each other, and we act in the interest of ENTSO-E, and we care about people, we work transversal, and we support each other, and we celebrate success, and we are a learning organization, and we explore new paths and solutions. So that was the end of the presentation.
Thank you, Knut. That was great. Thank you for walking us through that. And we do have time for some questions up to the top of the hour. I'd like to remind everyone, if you have any questions, please log in to slido.com and enter participant code ESIG28, ESIG28. Looks like we have 13 questions now, and the most popular that have been voted up, Knut, you had references throughout the presentation of a rock-off limitation. And actually, we had one that was just voted up as well. Let me get to the rock-off question. You mentioned a 1 hertz per second limitation. Could you explain a little bit more about what the root driver of that 1 hertz per second limitation is?
The root driver is that everything physical has to have time to react. First of all, if you're going to take action, do something, then you have to observe. That means you must have a measurement, and you have to estimate the values that you're going to act on. And everything takes time. So just to measure, to collect the measurements over a wide area or locally, you have to find out what's happening, calculate, and then you have to do action and send out control signals. So to be able to do everything, then you need time. And as you can see from the Iberian Peninsula example, okay, you needed 1 second. Everything happened in 1 second almost before the frequency started going up again.
Great. Yeah, thank you for walking us through that, Knut. We have another question asked by Fran. So Fran, thank you for participating and asking the question. Fran's question is, why were the inter-area oscillation events linked to power electronic penetration if they're rooted in synchronous generator characteristics? And I think the question was more around the frequencies of inter-area oscillations are typically linked with synchronous machine phenomenon. And what is the link to power electronic penetration with those inter-area events?
That, of course, those examples are maybe not fully representative for a system dominated by power electronics. But the Iberian Peninsula example, there you can see that there were considerable amounts of power, wind and solar in operation at the moment of the incident happened, when the incident happened. What we can see, one of the examples then for the oscillation was that you had a hybrid HVDC connector in a DC mode. And that started oscillations, and it kept oscillations going forever. But I agree that the other examples, there may be are more connected to the synchronous generator, but at the same time, more power electronics in the system will make every response will happen faster. And of course, we are afraid of resonances and converter-driven stability, that they are not interoperable throughout the system.
Okay, thanks for explaining that. There actually is a question that wasn't necessarily related, but you mentioned it in your last answer. The question is, what is meant by HVDC in AC mode? Could you explain that a little bit more?
I think that is, you try to evaluate or try to run the HVDC connection in mode that supports the AC grid. That's the best answer I can give. But I try to find out myself what exactly how you control the HVDC link then. In that way, what measurements are needed to do it in AC mode. And I think Rui Pastana can explain that better. If he
Sure.
is here.
Yeah, so we can take that as well and follow up with some more specific answers. Whether it provides things like active power control and frequency regulation on both sides for the AC grids, or voltage regulation as well. So that's a good question, and Knut, I think we can follow up offline to provide more detailed answers as needed.
Yes.
So thanks for walking us through that in a high level. So the next question, you gave an example of a wind plant instability in Norway. And for that example, do you know what the root cause was? Was it because of a weak grid condition? And do you know what the solution was to resolve that instability? Can you shed any light there?
Yes, it was a weak grid involved. It was on a radial, and the hydropower plant that usually is in operation on that radial was not in operation when the event evolved. And the wind farm itself was in this voltage control mode, so it measured the voltage then and took action. And of course, if you then measure one value, and the controller of the wind farm take action, and the next measurement is the opposite, then of course it will just fluctuate. To handle that, to mitigate that, it was necessary to do some changes in the control of the voltage controller. And then it's now working fine. But of course, this can happen everywhere. So it must be interoperable with the rest of the system then, under all conditions then.
Okay, thank you. The next question is, how is the symmetric and asymmetric inertial response different, and how can each be provided through grid forming converters? That's a very specific design of the converter question. I'm not sure if you can answer that exactly, but any thoughts you can share there between symmetric and asymmetric inertial response?
To be honest, no, I'm not able to answer that specific question.
Sure. That's something we can take back, Knut, and we can ask some of our members at ESIG to see if we can get a more specific answer on that. But thank you for the question. We'll follow up with you after the webinar. The next question, I think we already answered about the root driver of the 1 hertz per second limitation. Knut, you addressed that earlier, so we'll skip over that one since you already answered it. And the next question is ENTSO-E developing new stability tools for prediction of oscillations in high IBR systems in either the planning timeframe or near real time?
We are involved in different projects and activities then. And of course, all the TSOs in Europe are concerned with these topics. So there are a lot of software tools that can be used both in the planning and the operational time frame. and we can say that, okay, we are following and trying to develop the, we have the software and we try to develop models of the system. Of course, there are limitations on the computing time, for example, if we want to model the whole European system, then it will be challenging for the software tools to do such calculations. Quantum computing have been mentioned in this context.
Great, thank you for that. Our next question is about the wind generation again, when we had events, and it says, did the wind generation help the situation of bringing the frequency back to nominal? And how did the wind generating units close to the fault respond? For example, for LVRT, can you share anything there about the events that had wind generation and had the instabilities in the system?
Then you had to use the links provided in the slides here in the presentation. Go into the reports. There are tables with how the different production units responded throughout the events when we had the split of the European system. It's a very detailed description of what happened.
Great, thank you. We'll follow the links for sure. The next question was about the Iberian Peninsula tripping event. And it says, why did the pump storage in the Iberian Peninsula trip during the 24 July 21 event?
I guess that was a part of the system defense plan, or to trip that if you got the under frequency. It was in a pumping mode. So it meant that, okay, tripping it will reduce the consumption. So I guess it was a part programmed as a part of the system defense plan.
So it tripped on under frequency then?
Yes.
Got it. Okay. Thank you. And for the same example, for the Iberian Peninsula example, do we know which protection caused the IBRs to disconnect? Was it either a rock-off protection or fault ride-through, a ride-through event, or was it frequency again or any other protection?
Again, then, there are more specific tables in the report then. So something tripped on over frequency, something under frequency, and something on over voltage, under voltage. So the frequency measured throughout the system had huge variations also. So there were a lot of things happening in a very short time frame then.
Okay. Great, thank you. The next question relates back to some of the status of what's happening in ENTSO-E, particularly the RFG, and I'm not sure if you can comment on this or not, Knut, but are you able to talk about the latest status of the NC RFG 2.0 initiatives that require grid forming capabilities? Do you know if any of the TSOs are starting to shape grid forming requirements?
That's a question that I cannot answer and shall not answer.
Understand.
Yeah.
Thank you.
Because that's not a part of, we don't have a position or want to reveal any position of that at the moment.
Okay, thank you. The next question is the stability position paper publicly available, and where can we find it?
Yes, it is. You find it on the ENTSO-E website then.
Okay, great. And maybe what we'll do, we'll post a link to that in the response to the questions, so that folks can know where to download that.
Mm-hmm.
The next question is maybe more of a philosophical question, and it's we'll see if you can ponder on an answer with this, Knut. But the question is, why is so much emphasis put on the inertia when primary frequency response and fast frequency response are the only mechanisms arresting the frequency drift?
Well, Inertia is available instantly. It is there always, and it's reacting without any delay or anything. It's everything else, grid forming, there you have to do measurements and things like that. So they are by definition slower. You have to measure for a time period, even it can be 20 milliseconds or 60 or anything, but inertia is there instantly, and it gives you the time frame where you can react, where other capabilities can be issued then.
Yeah, in other words, it seems like the inertia, as you mentioned, is a key component of what the frequency deviation will do, especially in systems that have lighter inertia, have lower inertia relative to how the system responds with primary frequency response and fast frequency response. That's what I heard you say. So inertia is being a key component of the overall frequency response, and that's why we need to consider it, right?
Yeah, that's correct. And it's a response to changes in frequency, not to deviations in frequency.
Yeah.
So that's a key, the key then to the response from the inertia.
Yes, great. Thanks. This is a next question that I'm not sure you hit on a lot. I think you had one case study around this subject, but wondering if you can elaborate at all on which kind of models are needed for studying subsynchronous control interaction for wide area studies. Is that at all available either in the reports, or can you make any comment on that?
Yeah, subsynchronous oscillations, first of all, you have to be able to observe it. So you need at least PMUs. They have a sampling frequency of 50 Hertz, so they cannot monitor anything that is faster than that. And also you have to have higher sampling frequency to be able to cope with some of the subsynchronous phenomena. Then. So yeah, I don't know if it's the answer for the question. Actually,
yeah, I think that's. Thank you for elaborating. Let's look at the next question around grid forming again. It says, regarding grid forming capabilities, are the interactions between interconnectors and grid forming converters also of interest for inertial response? And I think the question might be alluding to that, is inertial response overall a part of the grid forming capability that should be considered between the grid and grid forming resources?
Well, grid forming resources try to evaluate the inertia. Someone will call it synthetic inertia, but of course it will never be exactly like inertia, but it can be programmed to imitate or the inertia in the best possible way. And the benefit of doing that is that, okay, you can give it a response that takes care of the best properties of the synchronous generator, but you also can remove the bad properties. You don't have to program it exactly like how a synchronous generator will respond.
Great, thanks for providing your input there. This next one I actually had to look up, but is the CGMES, or the Common Grid Model Exchange Standard, suitable for grid forming converters? Is there any limitation there? And are you able to comment on that? I'm not sure that you may be aware of the CGMES.
It's a lot of discussion and going around that topic. And of course, there can be some difficulties to exchange data for HVDC HVDC equipment, for example. It can be some secrets in there and intellectual properties that can be revealed if you exchange too detailed data and so on. So CDMS model can cover a lot then, but not all, I think, at the moment.
Okay, great. That's a good question. The next question, I think we can do maybe one or two more, relating back to rate of change of frequency. The question asks, what is the consequence of a rock-off event greater than 1 hertz per second? Or in other words, what is the rock-off relay threshold at 1 hertz per second protecting against?
It can protect against system splits, as showed then in Inertia 1 and Inertia 2 project. So if you get a rock-off of larger than 1 hertz per second in parts of the system, then the risk of system splits will increase.
Great.
So you have to keep the system together. You have to also be able to handle the rock-off and have local capabilities, local inertia, and local grid forming to handle it.
Yes. Okay, great. Our next question, Knut, and I'm not maybe exactly sure if this is something specific that's being talked about or general, but the question is, how do you see the role of the individual power plant on contributing to system stability by the self-adaptive and distributed manner? Is that familiar to you, or do you understand what they're asking about?
Oh, not actually, because okay, if you have a synchronous generation, then okay, then you have the properties of those. If you have power electronics connected devices, then okay, you have to cope with what's happening on your own bus bar, or you have to be able to respond then to in a pre-programmed way. So delivering and behaving like a voltage source converter, but at the same time you have to cope with, for example, phase jumps and things like that. So there are challenges to be solved still.
Yeah, absolutely. Maybe we can squeeze one final question in before we break for today. The question asks, do you have any reflections on how these services that you talked about could or should be procured in the future? Are they with codes and requirements? Are they with markets or anything else that you think would be beneficial?
There can be different opinions about that. Grid or market solutions can be suitable for some types of system services, while others have to be put into the grid codes. So I'll not say which properties should be in the one or the other. We know that in the UK they buy or they procure inertia on long-term contracts, for example. That's one solution. I don't have an opinion about what's the best way to do it. It depends, I think. So okay. I will not go into that.
Excellent. Thank you. Really great discussion, Knut. Really a pleasure to have you here. We have one more question about if there will be any future presentations regarding dynamic modeling for renewables or HVDC systems. And I would like to guide everyone back to the ESIG website. If you go to esig.energy and under the events tab, you'll see all of our future webinars that are planned, as well as looking at webinars that have already been given on that subject and any other subject. So esig.energy is the place to go. And since we're at the top of the hour, we'll wrap it up right here. Really want to thank Knut for your insight on the ENTSO-E stability activities, and also for your leadership of critically important initiatives to solve these needs with grids with high penetration of IBR. As I mentioned earlier, an email will go out once this recorded video file has been posted, and we'll answer any of the questions that we didn't get to or that we didn't know and we need to get some more information to get back to you on. We have another eSig webinar coming in just 2 days, this Thursday, covering grid planning for building electrification by Sean Morash at Telos Energy. For more information regarding all of our other webinars, like I said, you can look at our website at www.esig.energy, and under the events tab and under our newsletters and informal emails that are sent around to our membership as well. Knut, thank you once again for this timely and informative webinar. I want to thank all of you for your interest and participation today. We look forward to seeing you again soon. And in the meantime, everyone, please take care, stay safe, and thanks for your participation. See you soon.
Thank you.